on the properties of ionic versus molecular compounds. We've done our experiments. I've actually marked most of them that we did yesterday, which was great. We had time to submit it and hand it in. But I do need to talk a little bit about some of our observations. Your observations are I'm sure, are correct. If you saw that little light turn on, you wrote down that it conducted, and that's excellent. But in any experiment, whether the experiment is as simple as what we did yesterday or as complicated as, you know, a particle smashing experiment happening at the Large Hadron Collider, no matter how small or how big the experiment is, we always have what are called errors that creep into the experiment. They don't actually creep in. They're there, and it has many things to do with the equipment we use. Something is not functioning the way we expect it to. The beakers, the cleanliness of the beakers comes into effect. Did we dry out all of that tap water, right? So those are errors that can sometimes give us a misrepresentation of what the properties were supposed to be. And I noticed that in many of your observations. So I just want to write a summary for what I need you to know are the properties of ionic compounds versus molecular compounds. So my next slide here is just a simple chart. Ionic, molecular, the types of atoms we have in there, the conductivity as a solid, the conductivity in solution when it's dissolved, and then the melting point. So this is going to be our official information that you will use to study. I do want you to write this down. So what I mean is, some of your labs, you had a correct observation because that's what you saw, but because of an error, it's not an indication of what we would have saw if we had perfectly clean equipment. The electrodes on the conductivity meter were perfectly clean. So sometimes, like I said, due to maybe an effect of the equipment itself, or perhaps the procedure that we followed, we might not have cleaned things as well as we should have. We sometimes get a misrepresentation of what the observations are. Okay? So this is very much kind of like the chart that we've been taking over and over and over again. We will be eventually writing on the thing, or we can do it on paper. If you want a stylus, come up and grab a stylus. Again, I just asked, don't steal my styluses. I think I'm going to have to order some more. So, types of atoms for ionic compounds. What kind of atoms do we have to have for the compound to be ionic? What kind of atoms do we have to have? Yep. Metal and non-metal, one on the left and one on the right. So we have to have a metal and a non-metal. To contrast that, are molecular substances. What kind of atoms do we have if it is a molecule or a molecular substance? What kind of atoms did we have to have? Can't be a metal and a non-metal because we've already used that. What does it have to be? Two metals, it's got to be two non-metals. We'll talk about two metals. That's a good point. You could have two metals, right? What is that if it's two metals? We'll talk about that in a moment, but molecular are two non-metals. So non-metal and non-metal. Remember, they share their electrons. What is it called when we have two metals? Well, those compounds exist. What is it called? Yeah, very good. That's exactly what it is. We can mix metals together. You can melt them, mix them together, and then solidify them, and then you'll have a mixture of these metals. And when you do that, we have what are called alloys. Examples of alloys. Brass is an alloy. If you've ever seen that shiny orange kind of metal. It's a mixture of, gee, I want to say copper and zinc, but I'm not sure. I think it's copper and zinc. Other alloys. I'm trying to think of other alloys. Yeah, there's all kinds of them. Yep.
14-karat gold.
Yes, correct. Yeah. 14-karat gold is a mixture of gold and, is it copper? Oh, there you go. I didn't know that. I thought it maybe had a little silver in it. So 14 karat gold isn't pure gold. It's, I guess, got some copper and some gold in it, right? So that's an alloy. Why do we want to have alloys? They tend to have different properties than the original metals that we mix together. Gold itself is very soft. If you had pure gold, 24 karat gold, and you say you bumped it against something, you would actually put a dent in it very easily. By putting some copper with it, it strengthens it. It also makes it a little cheaper to make because you don't have pure gold, but it strengthens it so it becomes it's a little more tolerant to being bumped. So alloys are when you have two metals together. We didn't study alloys in this course, not a big deal. Two nonmetals, molecular. Okay, conductivity as a solid. We had the solid, we put the conductivity meter in it. Did the light turn on? It never did. The light never turned on for any of them. So we have here non-conductors. I'm going to put no and no. So as a solid, it does not conduct. Okay? Now, conductivity when we dissolved it. And this is where we had a few errors in yesterday's experiment, and that's why I wanted to clear this up. Conductivity for, well, we did molecular yesterday, so we did that very quickly. Let's do that one now. When we dissolved, say, sugar or the sucrose, and we put the conductivity meter in, does anybody remember? Yeah. Was it yes or no? Now, you may have seen that it was yes, but in actual fact, it's supposed to be no. Now, I'm not questioning what you saw, but you probably had a little error in your situation, all right? And I'll tell you how we can get an error on that. Molecular substances do not conduct in solution because they don't have little charges like the ions do. Remember, the ions have little charges, and when it dissolves, those little ions can move. Molecules like sugar don't have ions in them. So when you put them in the water, charges aren't able to move, and so they cannot conduct. How could we have got an error on that observation? Not that you did anything necessarily wrong. I'm just saying, what could have happened to give you a misrepresentation of the fact that a molecule is conducting?
Both sides, like both pieces of copper.
The conductivity meter maybe have touched each other. Yeah, it could have maybe accidentally touched. That's a good error, correct? What else could have happened? What if you cleaned it with tap water and then you didn't dry it completely? You just put the distilled water in with that little drops of tap water. What do we know about the conductivity of tap water? It does conduct a little bit. So if you had a little bit of tap water in there, those ions in the tap water might have conducted. You would have read it properly. You just were writing down what you saw, but an error could have come in, okay? So molecules, they don't conduct. Ionic? Yes, they do, because they have the ions in them. They have the charges in them. Melting point, very high for ionic, very high. Now, some of you guys said that some of the molecules melted very high yesterday with the hot plates. What was the highest temperature on those hot plates when you cranked it to the top? 550. The Bunsen burner, about 2,500, so about 2,500 degrees. So there's a great difference in the hot plate's temperatures than there is in the Bunsen burner's temperature. So we could barely get that one ionic compound to melt with the Bunsen burner very high. Here we could get these guys to melt with a hot plate, so we're going to say low. You might think 550 degrees is hot, but in actual fact, it's not very hot. All right? Okay, so there's our summary of what I need you to know in terms of the test. Some of our experiments were a little off of that, but that has to do with errors. That's not a big deal. Okay, so now we're going to do names and formulas of molecular compounds. Remember when we did ionic compounds, we did a crossover of the charges, and we needed to know what those charges were so we could cross them over. I might do a little bit of a review on that at the beginning of tomorrow's lesson, review period. Molecules are easy. You don't need to look at the charges. You don't need a periodic table at all to determine the names and the formulas of molecules. And that's because the name and formula system is built in. The amount of atoms are built in. Okay, so you can write that down. We use a prefix. We use that little word in front of a word. That's what prefix means, comes in front. And that tells us how many atoms there are. Nothing to cross over. If I have carbon dioxide, 1 carbon, 2 oxygens. So we have a prefix in front of the element. And there's only one exception. If there's only 1 atom at the start, we don't put a prefix on it. Again, my example, carbon dioxide. We don't say monocarbon dioxide. I don't know why. That's just the way it's kind of evolved as a language. Really, naming chemicals is like learning a little bit of a new language, the language of chemistry. So if there's only 1 atom at the beginning, we don't put mono on the front end. Okay? Now, the prefixes that we use, you may have seen in the past. My next slide is going to have a list of those prefixes. I do want you to write it down. But I also have a list of the prefixes on the periodic table. So when we do our test, that you'll be able to simply look at the chart on the periodic table, and you'll be able to see what the prefix is. Okay, it's right beside our polyatomic ions chart. Okay? So that chart, yeah, I'm sorry, I'm just looking at the clock. I'm trying to push a little bit. You guys are doing fine. I'm just looking at the clock. Yeah, 15 minutes. We'll be good. We'll get it done in 15 minutes. It's okay. I tend to get a little pushy when I'm watching the clock. I apologize in advance. Are we okay? Everybody good? So these prefixes, they look like this, and again, you don't necessarily have to make the big chart. The subscript in the formula and the prefix. And again, like I said, I've got a little chart on here. All right, so you don't have to memorize that chart. We just have to be able to use it. So one is mono. That's pretty obvious. Oh, maybe it isn't obvious. You know, you probably associate the term mono with the I think it's a viral kind of thing. But years ago, before they had stereo speakers, do you know what stereo means when it comes to music? It means you've got 2 different sounds coming out of each headphone. That's stereo. That's 2. Way before there was stereo, you only had 1 speaker. You know, back in the 50s, 1 speaker, and that was called mono. Right? That's the mono version of it because there was only 1 speaker. So mono, 1. Di, 2. Tri, 3. Those are okay. Tetra, that's a tricky one. Tetra comes from a prefix for 4. It has to do with a shape. This molecule's shape here, I showed you this the other day. This is called a tetrahedron because it has 4 triangular faces. It just means 4. Penta is not too bad, like a pentagon, right, in geometry, 5-sided object. Hexa, a hexagon. We don't say septa, we say hepta, all right, for 7, and octa for 8. There's a 9 and there's a 10 and all that type of stuff, but we're not going to use it, okay? So now at this point, once we get that list done, we're just going to practice naming a few from the formula. We're going to practice doing a few formulas. Then, like I said, there's a worksheet like we usually do to practice it. And that's all we're going to be then doing for today. And hopefully we can get done that sheet by quarter after. And then football people can go and everyone can get ready to do their thing. Okay? And I think everybody's done. Bella, you're looking at yours on your screen? Okay? Okay. So let's do some examples here. Let's do some examples. Like I said, for molecules, it's nice and easy. We are not looking for charges. We're not looking to cross anything over. We're just looking for those little words out front to tell us how many of those atoms there are. So, carbon dioxide. I'm just going to wait for a moment, let people get a chance to get it written down. You got it? What do you got? Carbon is what? Well, di is 2. You're focusing on the 2. But I still need the elements. I guess we do need a periodic table so that we can find out the symbols for the elements. C, O, 2. Oh, and you can see there that I've got a little animation of something coming up there. The di, tri, etc., etc. Oops, right there. You don't have to write that. You don't even have to write examples. Don't worry about that. So, nothing on the front means 1. 1 carbon, 2 oxygen. Phosphorus trichloride. Pat, what do you think? PCl3. And I'm hoping you're thinking this is a yawner. This is an easy one. Because it is. PCl3. Dinitrogen pentoxide. Dinitrogen pentoxide. What do you think, Josh? So, the di means what? Two. 2 of which element? Nitrogen. What symbol for nitrogen? Nope, it's not Ni. You're close. That's nickel. Ne? Nope, that's neon. You're running out of options. You got one more. N. So, N, and because it's di, what am I putting down here? 2, oxygen, symbol. Josh? O. And what does the pent tell me to put down here? Nope, that's oct, pent, 5. Excellent. Okay? Find the element, put the number, find the element, put the number. Okay? All right. Let's do a few back the other way. So there, again, you don't need to draw the chart. There is the formula. And now we're going to write the names. We'll let everyone get kind of caught up there. That's an SO3 for those of us who are visually challenged because we don't wear our glasses. And that's an N2H4. And that's a Cl2O. Patience. We're going to let people, give the arm a rest for a minute. We're going to let people get a chance to write this down. Like you. You write it down? Oh, you did. Good. What element is S? Here, I'll let you look at that. Go ahead, give it a shot. You don't have to wait for me. Okay, Pat, you can have the first one. What do you got? Sulfur trioxide. We don't put mono on the front. It never starts with mono. If there's only one and it's a second one, then we use mono. But if it's on the front and there's only one, we don't put it in. Sulfur trioxide. Okay? Kay, did you have an answer for 2? I know you wanted to answer 1, but have you got one for 2? Nitro. Now, it's the first one, so we don't put an "ide" on it. "Ide" only goes on the end, right? Nitro. What is that element called? Nitrogen. Dinitrogen. Dinitrogen. Tetra. Nope. What's an H? What's H? hydrogen, but we've got to have that "ide" on the end. So how do you think it's going to sound? So so we have nitrogen and it becomes nitride, but we're not doing that. Hydrogen becomes hydride. Hydride. Tetrahydride. Hydride. All right? Excellent. Last one. Yep, Eric. Dichlorine. Dichlorine. Oxide. It's got a 1, and it's not on the front, so we have to put a mono in front of that one. Monoxide. We actually don't put the 2 O's together. We just put monoxide. But if you did put an extra O in there, I wouldn't mark it wrong. That's monoxide. Dinitrogen monoxide. Okay? And I'm just looking ahead here. Note. What is the note? Yeah, I actually do have one more thing I do want you to write. All right, whoops. Some molecules have their own names, and I do want you to write those down. These are molecules that just have their own names. There's one more important one on there that has its own name that I don't have on there. We just have a common name for it. What other molecule could I add to this that has a common name? Oxygen? No, that's just O2. That's oxygen, but that's not the common name I'm looking for. What substance has a common name? We interact with it every day, all the time. Water. Formula for water? You're giggling because I said water like that? You're Mr. Williams? Yeah, I know. Mr. Williams, I always get that when I say it like that. Formula for water. H2O. H2O. All right. So we have some molecules that have common names, and they're good to be aware of. Ammonia, used as a fertilizer, right? If you're side dressing corn, or if you live on a farm and you're putting that anhydrous ammonia into the ground, that's the chemical that you're using right there, NH3. Ozone protects us from getting burnt. It's way up in the atmosphere. It can be produced by sparks. So during a thunderstorm, if there's a lightning, it'll produce a little bit of ozone. Methane, that's what we use in our natural gas. So if you've got natural gas coming into your house that heats your house, our Bunsen burners burn methane. And then obviously we have water. Okay, so that's the end of the lesson itself. So at this point, you can go to Google Classroom. You can open up the worksheet associated with today's lesson, and there's just a bunch of practice problems on there. We'll work at that for about 10 minutes, and then we'll get ready for doing our thing. So if you need a stylus, you can come and grab one, and yeah, we can work on that. And you can put these practice ones on paper as well if you don't want to work on, if you don't want to work on the screen, you can work on paper as well. You guys know that. Okay, I'm going to stop the recording here.